In this video, we're going to introduce section 4 on alkanes and cycloalkanes, which is found in chapter 4 of your text. Specifically, we're going to discuss sections 4.1 and 4.2, the introduction to alkanes, followed by the nomenclature of alkanes. Now, alkanes represents the first functional group that we will discuss in this course. And alkanes are a part of a larger group known as hydrocarbons. And hydrocarbons are compounds comprised of just carbon and hydrogen. And so we typically think of hydrocarbons as not only our alkanes, but also alkenes, alkynes, and with certain aromatic ring systems. Now, hydrocarbons that lack pi bonds are typically referred to as saturated hydrocarbons or alkanes. Unsaturated hydrocarbons are often of these varieties. They could be alkenes, alkynes, or other aromatic systems. So as an aside, the main source of alkanes is petroleum. Petroleum is a complex mixture of literally hundreds of hydrocarbons, most of which are alkanes. So as shown in table 4.5, there are various industrial uses of petroleum fractions. We see that the smaller hydrocarbons are typically those that we derive from petroleum to give us natural gas and solvents. Somewhere middle of the range, we have our gasolines and our jet fuels. And then the higher fractions that are typically separated out during the refining process give rise to our diesels and our tires and such. So the process of separating crude oil into these commercially available products, this is called refining. And the gasoline fraction, interestingly, only represents about 19% of our original crude oil. However, with cracking and reforming, this increases the yield from 19 to 47% for every barrel of crude oil that we extract. So in section 4.2, we're going to look at the nomenclature of alkanes. And nomenclature is a system for naming organic compounds. So it's very important in this course that we have a systematic approach for naming organic compounds. And this approach was introduced to you in Chem 104 in the naming of alkanes. We're going to go through this again in sufficient amount of detail, and then we'll apply the same set of rules in the naming of other functional groups as we proceed through the various sections. It's very important to have a systematic approach to the naming of organic compounds. Unlike in the early days, organic compounds were often named at really the whim of their discoverers. Unfortunately, some of these common names still persist today, but what we'll show you in this section is that there's a systematic approach that we can use to name any organic compound. So the systematic approach that we use to name organic compounds is often referred to as the IUPAC system. So names produced by the IUPAC rules, these are called systematic names. Ideally, every possible organic compound should have a name from which an unambiguous structural formula can be drawn. Now, different names for more than 16 million known organic compounds are possible using this systematic approach. And that's the approach that we'll go over in this section. So the systematic approach involves 4 discrete steps that are required when assigning the name of an alkane. We first have to identify the parent chain, then identify and name any substituents attached to that parent chain. We number the parent chain and assign a numerical locant to each of those substituents, and then we arrange everything alphabetically. And so we'll go through each of these 4 steps in detail when we name alkanes. So the first step is to identify the parent chain. By that we mean we need to choose the longest continuous chain of carbons in our structure. So if we look at this example, we can see that the longest continuous chain of carbons, highlighted here in red, has 9 carbon atoms. And so this parent system would be a no-name system. What's not highlighted in red, these will be the substituents attached to that parent chain. So you can see we'll have substituents of different shapes and sizes and chemical makeup. In this example, we have what's referred to as a methyl group, which we'll talk about in just a moment. And here's a 2-carbon substituent, which we'll refer to an ethyl group. And in this system, this structure, we actually have 3 ethyl groups associated with this alkane. So once we identify the number of carbons in our parent, we have to use one of these terms to represent that particular number of carbons. So if it's 1 carbon is our longest chain, that would be meth. And the suffix for all alkanes is ane. So if the structure has 1 carbon atom, the name of the alkane, the unsubstituted parent, would be methane. If it's 2, ethane, and so on. And so for this course, it's important for you to remember the first 10 parents for the alkane family. Now, when identifying the parent chain, there can be situations in which you may encounter 2 chains of equal length as potential parents. So when choosing the parent chain, it should be the chain with the greatest number or greater number of substituents. And as we highlighted in our previous example, substituents are these groups that are connected to the parent chain. So in this example, there are 2 possible parents, each 7 carbon atoms in length, that could be the parent for this particular structure. On the left, we see that if we have a parent chain as shown in red, we're left with 3 substituents off that parent chain: a methyl group, an ethyl group, and a second ethyl group. Whereas if we were to make this particular continuous chain of carbons our parent chain, we would only have 2 substituents, what's known as an isopropyl or 1-methyl ethyl group, which we'll get to in a moment, or this ethyl group. So because there are only 2 substituents off this parent, this would be the incorrect parent to choose when naming your alkane. So when naming an alkane, if you have the potential for 2 different equal length parents, choose the parent chain that has the greatest number of substituents or the greatest amount of branching. So it's very important early on to identify the correct parent chain, because not doing so will lead to a name that is incorrect. Now, if we have cyclic structures, such as those shown here, these cycloalkanes, how we indicate that in our naming system is we use the term cyclo to indicate the presence of a ring in the structure of an alkane. So if we had a 3-carbon system as shown, this would simply be propane. But as a ring system, we use the term cyclo to represent that it's a cyclic system. Similarly with butane and pentane, if it's actually a cyclic system, unlike the open chain acyclic system, we would use the term cyclo to represent the cyclic nature of this compound. So we generically refer to these compounds as being cycloalkanes. So once you've identified the parent chain, we then identify and name any substituents attached to that parent. And so as you can see in this example, what's highlighted in this orange color is the parent chain. What's highlighted in green are the substituents attached to that particular parent chain. So the next part of our naming process is to give names to these individual substituents. So substituents are named with the same terminology used for naming parents, only we replace A and E with YL. And these groups are generally called alkyl groups. But specifically, we'll use the terminology, as we just said, similar to the parents, in that if we have a 2-carbon substituent, this would be referred to as an ethyl group. If we had a 3-carbon substituent, this would be referred to as a propyl group. And so we use the same type of terminology, except we use YL as the suffix as opposed to A and E. So in our example, the groups highlighted in green, we start our counting for the number of carbons in that alkyl group from the first carbon directly attached to our parent. And so in this example, this would be carbon 1 of the ethyl group, and this would be carbon 2 of the ethyl group. But the total number of carbons, the total number of continuous carbons in this particular substituent is 2. And so we would refer to this as an ethyl substituent. Similarly, we have a 1 carbon attached to the ring at this location, and so that would be referred to as a methyl group. And in this example, the first carbon of that alkyl group is here, and the longest continuous chain would be 1, 2, 3. And so we would identify this alkyl group as a propyl group. Now, when you have structures that contain both a ring and an acyclic part, you have to decide which is the parent. And so the rule of thumb is that a ring is treated as the parent when the alkyl group connected to the ring has an equal or lesser number of carbon atoms than that found in the ring. So in this particular example here, we see that we have a ring system. This is known as cyclohexane. And what would be attached to this ring system is this particular substituent. The substituent is 1, 2, 3 carbons long, whereas the ring system contains 6 carbons, i.e. hexane. So when the number of carbons is equal to or less than the number of carbons in the ring, then we would refer to this compound, the parent of this compound, as being the ring system, cyclohexane. So what's attached to this ring, of course, is this 3-carbon substituent. This is propyl, propane, drop ANE, add YL. And propyl cyclohexane is the full name of this compound. Now, just to comment that there should be no space, not that there's a large gap between propyl and cyclohexane, but when we write out this word, propyl cyclohexane is all one word. There's no syntax or spaces between the L and the C as well. I'll also point out, and this will be something we'll cover a little bit more later, but we don't have to provide a locant as to the location of this ethyl group on the ring because there's only a single substituent. If there were 2 substituents, we would identify the location of those 2 substituents with respect to one another. It could be 1, 2, 1, 3, 1, 4, for example. But in this example, the locant is considered unnecessary or redundant, and we never want to include redundancy in our IUPAC names. Now let's look at another example where the ring system actually has fewer carbons than the acyclic or linear part of the molecule. And so you can see in this example, the ring only has 3 carbons, 1, 2, 3. That would be cyclopropane as a parent. But as a substituent, we would drop the ANE and add YL, so that becomes cyclopropyl. And we do so for this example because we have 1, 2, 3, 4 carbons in this acyclic part of the molecule. So that 4 butane, so but is the parent, ANE represents the suffix for alkanes, and so butane becomes the parent because there's greater number of carbons in butane, i.e. 4, versus the number of carbons in the ring, which was 3. And so again, I'll write this out to be more specific, but this would be drawn without any spaces. And so the name of this compound is 1-cyclopropyl-butane. Now, no space between the L and B in cyclopropyl and butane. This time we do need to indicate a locant, and we'll get to that in just a moment. But the reason for that is that we could have the cyclopropyl group at this position, which would be then a 2-cyclopropyl butane. And one last point is that in this example, they do use a capital C. That is an optional component. Generally, we don't capitalize the names of organic compounds unless they begin a sentence. So the last thing I want to discuss with respect to the identity of substituents is how do we name branched alkyl substituents? These are more complex than naming straight chain or linear substituents. So the examples we saw previously, when we referred to propyl, butyl, pentyl, these referred to linear substituents that were either 3, 4, or 5 carbons long, respectively. But if we have branching off those particular alkyl groups, how do we deal with that using the IUPAC system? Well, first thing we do is we start to number the longest continuous chain of carbons that are found in that alkyl group. And so as you can see in this example, this is our parent system, what's highlighted in red. And so it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Undecane, not responsible for that. You're only responsible from 1 to 10. But nonetheless, we can see that at this position, we have a substituent that has fewer carbons than the parent, as you would expect. So when we're numbering this particular parent of the alkyl group, we always start here as carbon 1, as I mentioned previously. So this will always be carbon 1 of the alkyl group. And then we're looking for the longest continuous chain of carbons in this particular alkyl substituent. So 1, 2, 3, 4 is highlighted here. So that would be a butyl. So the parent for the alkyl substituent, the complex substituent as we often refer to it, the parent is 4 carbons long, so that will be butyl. Now at position 2, using the same numbering pattern that we just identified, at position 2 we have what we call a branch point. We have a splitting, if you will, off that parent. And so attached to position 2 of this alkyl group is the single carbon. And so single carbon, 1 carbon, meth, it's a methyl group. And so the complete name for this alkyl group would be a 2-methyl-butyl. And we'll show you later on when we put that into the name, we have to identify it as a complex substituent by encapsulating it in parentheses or brackets. And so we have an open bracket, 2-methyl-butyl, closed bracket. And that identifies to the reader that it is a complex substituent off the parent chain. What's not being discussed in this particular example is that you also have to identify where that branching occurs on this particular parent system. So 1, 2, 3, 4, 5, 6 from this end, 1, 2, 3, 4, 5, 6 also. So this would be considered a 6 hyphen open bracket 2-methyl-butyl closed brackets and undecane. Again, we won't be testing you on anything greater than 10, but in this example, there were actually 11 carbons in that parent system. So as you can see, how we treat the complex substituent is we place parentheses or brackets around it to indicate that it is a complex substituent, and the locant, which I'll discuss more in the next few slides, it's presented in front, and what's between the 6 and the open bracket is a hyphen. We're always going to show in our names hyphens to break between a number and a letter, and we sometimes will use commas between numbers. We'll discuss that in just a moment. Now, some complex substituents also have common names, and these common names are accepted by IUPAC. So when we're asking you to provide an acceptable name, an IUPAC name, you can use common names in that particular naming system. And we'll give you a few examples of those right now. But if we ask for a systematic name, that implies that we do not want the use of common names. So that might be a small variation that you'll observe in some of your YA Plus assignment questions. Nonetheless, here's an example of a complex substituent that has a common name with it. And we're only going to look at the 3 and the 4 carbon systems for common names. So that will give us a total of 4 common names that represent alkyl substituents. So as you can see in this example, a 3 carbon system, if this were some generic parent, and in branching off that we had 1, 2, 3 carbons, we would refer to that as a propyl group. Now, what's shown in this dotted square or rectangle is that we have a situation where we again have a group which has 3 carbons in it, but you can see that the connectivity to the parent is at the mid carbon in this chain, so carbon 2. So this is often referred to as an isopropyl group. So isopropyl is the common name associated with this particular arrangement of carbons and hydrogens. Now we can approach this from a systematic manner using the IUPAC naming system, just like we saw in the previous example. So in that way, we would number, if you wish, for just clarity, if we were to number the longest continuous chains in this particular substituent, we would start our numbering with the first carbon directly attached to the parent. That will be carbon 1. And you can see whether you go in the upwards direction or downwards direction, the longest chain will be 2 either way. And so how we would name this using the systematic approach is that the longest chain is 2, so that gives us ethyl. That'll be the parent for the alkyl group. But we have a branching at carbon 1, and attached to that is a methyl group. So this is often referred to as a 1-methyl ethyl using the systematic IUPAC naming system. But if you were to provide a common name, this is known as isopropyl. Using isopropyl, the I is alphabetically relevant, as I'll mention in just a moment. That's not always the case with the common names. And you do not need to set this off in brackets. The brackets are only used to designate a complex substituent which uses the systematic naming approach. Now here's some examples of branched alkyl groups where there are 4. Total number of carbons in the substituent is 4. So the linear substituent is butyl, but we have 3 variations of that butyl in the sense that there can be different arrangements of those 4 carbon atoms. So if we have this particular arrangement of those 4 carbon atoms where carbon 1 ends up being a branch point where we have ethyl group in one direction and a seemingly methyl group in the other, this is referred to as a sec butyl. A secondary butyl is where it's derived from, sec meaning 2, and so there's really 2 groups attached to that branching carbon from the parent chain. Now, how we would approach this from a systematic angle is that this would be carbon 1, as always, and when the longest chain would be 3. And so this would be a propyl. This would be the parent of that alkyl group. And the branch point occurs right at carbon 1, so this would be a 1-methyl propyl. And again, we'd use brackets to indicate that that is a complex substituent. So sec-butyl or 1-methyl propyl are both acceptable names, but the systematic name involves 1-methyl propyl, and the common name is sec-butyl. Sec is italicized. I'm not going to concern myself with that when you're typing out names. The system should accept the unitalicized version, but just for clarity, SEC is italicized, but it's not alphabetically relevant as a result. So that's one distinction that we'll see. In the next example, this is isobutyl, and the systematic name would be 1, 2, 3. Propyl would still be the longest continuous chain of carbons in that alkyl group, but now the branching is occurring at carbon 2. So this is a 2-methylpropyl. That's the systematic alkyl substituent or complex substituent, and isobutyl is the common name. Very similar to isopropyl in that the second last carbon is a branch point where you have 2 methyl groups attached to it. Very similar to the isopropyl, except now it's extended by 1, and that branching doesn't occur at the first carbon, which is the isopropyl group, but at the second carbon. So it's a little bit further out. So our last example is the tertiary butyl group. Here we have a alkyl group complex substituent, which we have branching off the first carbon, 3 methyl groups off that first carbon. And so that's tertiary, meaning 3. That's where the tert butyl comes from. Tert is again italicized, so it's not alphabetically relevant. And how we would name that using the IUPAC system is that the longest continuous chain of carbons will be now 2 in any of these 3 directions, and branching occurs from carbon 1. So it's an ethyl is your base, your parent, and we have 2 methyl groups off position 1 of that ethyl group. So this becomes a 1,1 dimethyl ethyl. And notice the syntax here, that it's a 1, 1, no spaces between the comma and the number. So it's 1, 1 hyphen dimethyl ethyl. And so this is the first example where we have 2 of the same substituents being shown in this particular alkyl group. And so instead of saying 1 methyl ethyl, it's a bit of a mouthful, we just simplify that by placing all the numerical locants together, separated by commas. So in this case, we have 2 numbers separated by a single comma. And then once the locants are stated, it's hyphen, and we use what we call a multiplier prefix to indicate the number of methyl groups associated with those locants. So it would be incorrect to say 1,1 methyl ethyl, because you're not being super clear on why you have 2 locants. Every locant indicates a particular group, and every group must be identified by a locant. So we don't say 1 methyl, we collapse that to 1,1, and we have to say dimethyl. We need to include that multiplier prefix. And the 1,1, the D in dimethyl, is alphabetically relevant, as we'll see when it's a part of a complex substituent. But we'll see when we look at other examples that when that multiplier prefix lies outside of the brackets, it's not alphabetically relevant. So there are a few things with the IUPAC system that take some getting used to, but that is how the system works. And don't shoot the messenger. I'm just trying to show you how we get through this and how we name these compounds in an unambiguous way. So now the third aspect that we need to consider is we have to number the parent chain. And we've already seen this a little bit in our previous examples, but now we'll specifically talk a little bit about it. So we need to assign the parent. We have to identify where that is in our structure, but then we have to number it. And that will allow us to assign a locant to each substituent found attached to that parent. So as shown here, in order to assemble the systematic name of an alkane, the carbon atoms of the parent chain are numbered. And these numbers are used to identify the locations of each substituent. These numbers are called locants. So in this example of methylpentane, you can see that 2-methylpentane is drawn differently than 3-methylpentane, and that's because that methyl group is found at a different location on that pentane chain. So when we're numbering the parent chain, if one substituent is present, it should be assigned the lowest possible number. And so in this example, we see we have a 7-carbon parent system. This would be heptane. So heptane, 7 carbons in length, has a methyl group at this location. Now, if we number from left to right, we have 1, 2, 3, 4, 5, 6, 7, and this methyl group is located at position 2. And so this would be a 2-methyl heptane. So 2-methyl, all one word, heptane. Shown to the right here is an incorrect way to number the parent. Doing it in that way, we would have our methyl group at position 6. 6 being a larger number than 2 would be the incorrect way to identify the locant for this particular compound, or the locant of this particular methyl group in this compound. So 2-methyl heptane is the correct way to name this particular structure. You always want to give the substituent the lowest possible number. And we'll see that if we have multiple substituents, you're always trying to determine what's the lowest possible set of locants to describe the location of those groups. And so we'll see examples of that shortly. So here's an example of that right now, where we have multiple groups, multiple substituents. And so we have to assign numbers so that the first substituent receives the lower number. And this becomes a comparison that you need to make, that you order those locants that represent the placement of those substituents from lowest to high, and you compare the locants one by one. So in this example, we could number this as a 2,5,5 trimethyl heptane or a 3,3,6 trimethyl heptane. But what really matters is what's shown in these green boxes, is that when you compare the first locant in this possibility and the first locant in this possibility, 2 is lower than 3. And so therefore, this is the set of locants that you would go with. So let's write this one out. So in this example, we have a 2, comma, no space, 5, comma, no space, 5, hyphen, and because there are 3 methyl groups in this structure, we have to use the multiplier prefix for 3, which is tri. So it's di, tri, and tetra. That will probably be all that we'll need in this course. Tri, no space, methyl. And again, the parent is hept, and it's an alkane, so ane is our suffix. So 2,5,5 trimethyl heptane is the name of that structure. So as I just mentioned, if there is a tie, and in this example there is, that we have a methyl group at the 2 position regardless of which way we number the parent chain, in order to determine which set of locants takes precedence, you would then look to the second locant in that set, and 3 is lower than 5, so this set of locants would be the correct set of locants. And so similar to the last example, last name, this would be a 2,3,6 trimethyl heptane. Now when it comes to numbering ring systems, the same rules apply. So in this example, you can see we have a 6-membered ring, 6 carbons in this ring system. So that would be 6-hex, it's an alkane, ane, hexane, but it's a ring system, so it would be cyclohexane. So cyclohexane is the parent because it has a larger number of carbons than any substituent off that ring system. And so this would be a trimethyl cyclohexane, but how would we number this? Well, there's 2 possibilities. We could start our numbering here or here. And so if we start from, let's say, this position and go clockwise, we would have 2 methyl groups off the 1 position and a 3rd methyl group off the 3 position. So that would be 1, 1, 3 would be the set of locants for that example. If we were to number it in the opposite direction, it'd be a 1, 3, 3. So those are the 2 possibilities. And again, you can see that the first locant in either possibility is identical, and so you go to the next, and that's where we see our first point of difference. We see we have 1 for the left-hand structure and 3 for the right hand. So if we were to name this particular compound, this set of locants would be used to describe this particular organic molecule. So let's draw that out or write that out. So that would be a 1, comma, no space, 1, comma, no space, 3, hyphen, tri to represent the multiplier prefix that we have 3 methyl groups, 3 identical substituents off this ring, and no space, cyclohexane. So that's the name of this particular cyclic structure. And just one last point that we've already made in these last few examples is that when a substituent appears more than once in a compound, a multiplier prefix is used. And so again, we've already looked at this particular example in detail, but just to highlight again, I'll hide this, that hyphens are used to separate numbers and words, while commas are used to separate 2 numbers from each other. And again, in rare instances, we'll have spaces, but we won't see those cases or those examples until we get into our last section of this course. For the most part, it's a continuous string of numbers and letters and a little bit of syntax that describes the IUPAC name for organic compounds. Now, the last part of the naming of alkenes and naming of all organic compounds is that we have to arrange the parts of the name alphabetically. So if you have multiple substituents, we have to know how is it that we order those particular substituents, and it's based on alphabetical order. So once all substituents have been identified and assigned proper locants, they're placed in alphabetical order. Now, prefixes such as the dis and the tris and so forth, these are not included as a part of the alphabetization scheme. They're only alphabetically relevant if a di or a tri, for example, is included in a complex substituent. Similarly, the sec and sec-butyl or the tert and tert-butyl, these are also ignored for alphabetation purposes. However, iso is not ignored. So in sec-butyl, if you were to alphabetize sec-butyl, if you were to use an acceptable name, and you decided to use sec-butyl, when you would alphabetize this particular group, it's the B in butyl that is considered alphabetically relevant. While if you had a common name isobutyl being used in your name, it's the I in isobutyl that you would use. And again, iso and isobutyl is not italicized, and so that's one way to distinguish those particular groups. So the tertiary butyl, if you were to alphabetize these 2 groups in the same name, for example, of the structure, it's the B that's alphabetically relevant, and it would precede the E in ethyl. So it would be a tertiary butyl ethyl. But if you had ethyl and isobutyl in the same structure and you were arranging those groups in alphabetical order, the E in ethyl would take priority, obviously alphabetically, over the I in isobutyl. So please keep those alphabetization rules in mind when naming alkanes and cycloalkanes. So in summary, there are 4 discrete steps that we must go through when assigning the name of an alkane. The first was to identify the parent chain, so we choose the longest chain, and for 2 chains of equal length, the parent chain with the greatest number of substituents should be chosen. Once you identify the parent, everything else is considered a substituent, and so we need to name those substituents. We also need to, thirdly, number the parent chain, and so we number the parent chain and assign a locant to each of those substituents. And we always will give the first substituent the lowest possible number. If there's a tie, meaning there are substituents from either end, if you will, of that parent chain, then the second substituent has to have the lowest number. So to choose the lowest set of locants, that's the manner in which we go about doing that. And then once we have all the substituents named and numbered, and we identify the parent and the suffix, then we arrange everything, all the substituents, alphabetically. And please note that we need to ensure that the locant precedes each of those substituents. So there's hyphens used between letters and numbers. And for identical substituents, we often will use the multiplier prefixes. So we don't refer to something as a 1-methyl, it's a 1,1-dimethyl, as we saw in a previous example. So let's look at a couple of examples of how we go about naming an alkane. So in this particular structure shown here, the first thing we must do is identify the parent. And so step one, you can see that in this example, what's shown in red has been identified as the parent of this system. It's the longest continuous chain of carbons. And so if we were to count that, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons in this particular chain. Okay, so 8 carbons is going to give us the parent oct. It is an alkane, so the suffix will be ane, so it's an octane will be our parent system. Now, also what would catch the eye would be this continuous chain of carbons as well. So we can count that 1, 2, 3, 4, 5, 6, 7. It's 1 carbon shy of the longest chain. So this would not be the parent. The parent is what was shown in red. Once you identify the parent, then as shown in this example, we need to identify all the substituents. And so we see we have a methyl group here, a methyl group here, and a 2-carbon alkyl straight chain alkane alkyl group, the ethyl. Okay, so we're going to have dimethyl associated with this as well as an ethyl group. So we'll have dimethyl as a part of our name, and we'll have ethyl as well. All right, so once we've identified and named the substituents, we then assign locants to these substituents. So we have to count that if we start from this end of our parent, 1, 2, carbon 2, we have our first substituent. If we start from this end of the parent, 1, 2, 3, 4, 5, our first substituent is found at position 5. So 2 being lower than 5, we'll number the parent as shown in this example. So we're going to number, this is carbon 1, and this will be carbon 8. So now we can identify the location of our substituents. We have a 2 and 3 to identify the methyl groups, and at position 4, we have the ethyl group. So we can include our locants. It's going to be a 4 ethyl, and for the methyls, we're going to have a 2, 3 hyphen dimethyl. And so these are the 3 parts, if you will, of the name. We have our parent, we have our methyl substituent summarized here, and we have our ethyl substituent summarized there. And so now it's a matter of alphabetizing these particular substituents in our final name. And so when we're alphabetizing these 2 substituents, recall it'll be the E in ethyl, that's straightforward. But when it comes to the dimethyl, recall that the multiplier prefix is not alphabetically relevant unless it's a part of a complex substituent. So in this example, it's the M in methyl that's alphabetically relevant, and you use that letter to decide where it's placed in alphabetical order. So the E will precede the M in methyl, and again, it could be confused that the D would be relevant, but it's not relevant unless it's a part of a complex substituent. So as shown, we can see that our final answer, or final name for this particular structure, is a 4-ethyl hyphen 2,3 hyphen dimethyl octane, all one word. So let's look at one more example. Let's name this particular alkane. So again, the first thing to do is to identify the longest continuous chain of carbons. In this structure, we have not only an acyclic part, but we have a cyclic part to this molecule. And so we could start by counting the number of carbons in our ring system. And so we have a 1, 2, 3, 4, 5. This is a cyclopentane ring. It could be the parent if there are substituents that are fewer than 5, but anything greater than 5, we would not treat the ring system as a parent. So let's look at the acyclic part. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So here we have two possible parents that are 6 carbons in length. So at the very least, we know that this ring system will not be the parent because we have more carbons in our open chain or acyclic system. So in the acyclic part, 6 carbons. If this were the parent, we would have 2 substituents. If this were the parent, we would also have 2 substituents. But regardless of which parent you choose, you'll end up with the same name, because in either instance, if this were the parent here, this will be an ethyl group. If we made this the parent, it would also be an ethyl group, and at the same position off that parent. So let's write out some of this information. We have a 1, 2, 3, 4, 5, 6. We said 6 carbons. So that's hex. It's an alkane, and so ANE to represent that. That's the suffix. So let's identify our parent, just for clarity. So everything off that parent is considered a substituent. So we have an ethyl group, and we have the cyclopentane ring, so this becomes the cyclopentyl. So we have an ethyl group, we have a cyclopentyl group, and now we must number our parent chain. So if we start counting our carbons from the left-hand side of the structure, 1, 2, 3 becomes the first branch point, or the first point where a substituent is located. If we start from the opposite end, 1, 2, 3, it's also 3. So in this example, 3 could be used for ethyl or cyclopentyl. So in a scenario like this, what gives precedence is alphabetical order. So because the C in cyclopentyl is first in alphabetical order relative to the E in ethyl, we're going to assign the cyclopentyl with the locant 3. And so therefore, that would give the ethyl group the locant 4. So now we need to alphabetize everything. And so again, it's the C in cyclopentyl that is alphabetically relevant, and the E in the ethyl group. And so we will organize all this together. So it's 3 hyphen cyclopentyl hyphen 4 hyphen ethyl hexane. So 3 cyclopentyl 4 ethyl hexane would be the proper systematic IUPAC name for this particular structure. So if you have any questions about the naming of alkanes, please email me or start a discussion in our forum. Thanks for listening.